All right, so our first derivative is 7 over divided by 6 plus 2 squared. Let's go back. That's our third step. So fourth step, we want to set up our sign diagram to include our vertical asymptotes and any, obviously, points that we would have found with our first derivative and second derivative when you set it equal to 0. So here's what we need to test now. If I set 7 divided by x plus 2 equal to 0, I have a constant divided by an expression, a quadratic actually, x plus 2 squared, quantity squared. If I set this equal to 0, is there any way that I can have a fraction with a constant as a numerator equal 0? The only way to get a fraction to equal 0 is if the numerator is equal to 0. It's not going to be possible. If you do it algebraically, so let's say I multiply both sides by x plus 2 squared, quantity squared, well, I'm going to come out with 0 multiplied by x plus 2 quantity squared. So now I have 7 is equal to 0. That's not true. So I actually don't have any points of inflection here. So I can, though, check my second derivative, and I will do that as well because I do want to include my second derivative. So I'm going to start to set up my sign diagram, but I want to take my second derivative first just to make sure I am not missing anything. So let's go ahead and find the second derivative. Derivative of the numerator is 0 multiplied by the denominator, and subtract the derivative of the denominator. So chain rule here, 2 times x plus 2 now drops to the power of 1 multiplied by the derivative of the inside function. So that's 1 divided by my denominator, x plus 2, quantity squared squared. So now I have to the fourth. All right, so let's extend the page here. If I wind up simplifying this and setting it equal to 0, I'm going to come out with a similar case here. So I am going to go ahead, that's 0. So now I have negative 2x and minus 4, okay, divided by quantity x plus 2 squared, or to the fourth, excuse me. When I set that equal to 0, again, what I'm really interested in is my numerator being equal to 0. And I wind up seeing that there is a change in my inflection, in my concavity, excuse me. My concavity changes from either concave up to concave down or concave down to concave up. If this is negative 2x minus 4, I'm going to add 4 divided by negative 2. So x is equal to negative 2. That's where that changes. If I look back up to the top, x equals negative 2 is also my vertical asymptote. So that means that wherever that vertical asymptote is, we have a change in concavity. Let's go ahead and set up our sign diagram, and then we'll put all this information on the graph. And I'm going to come up a little bit here. Okay, so this is kind of my combination of step 4, 5, and 6 here. I'm going to go ahead and set up my sign diagram. And I always want to immediately write f prime and f double prime, first and second derivative here on the left-hand side. That reminds me that when I choose a test value, I'm reminding myself to substitute into f prime or substitute into f double prime. The values that I'm going to put across the top here, I want to include any critical points that you found when you set your first derivative equal to 0. We did not have any here, so I will not be able to include those. And I also want to include any points of inflection. Well, I found negative 2, and negative 2 also happens to be my vertical asymptote. So I am going to put here vertical asymptote just to remind me that this is at negative 2. What I'd like to do is I'd like to pick a test value to the left of negative 2. So somewhere between negative infinity and negative 2, I'd like to pick a test value. And then somewhere between negative 2 and infinity, all the values to the right of negative 2, getting larger than negative 2, I'd like to pick a test value in there as well. So my test value, any number at all. So let's pick an easy one. I don't know, negative 3. That works. And then between negative 2 and infinity, again, another easy one, maybe 1 or 0. Something simple that we can use. This is our test value, our test number. Okay? The test number gets substituted into our first derivative for the first derivative test to check whether we have an increasing or decreasing function. And it also gets substituted into our second derivative to check whether we have concave up or concave down at those points. So I'm going to go ahead back up and I'm going to take my, I'll use green for this, that works. So I'll take negative 3, substitute it into my first derivative. If I have negative 3, substitute into my first derivative. Negative 3 plus 2 makes negative 1, square it, positive. So 7 divided by a positive number will give me a positive for my first derivative test. That means I am increasing. So my function is increasing, and I'm going to draw a little increase here. That's what my function is doing right now. Take my test value of 1, substitute into the first derivative. Again, I will get a positive value. So I'm actually increasing as well here. Let's see what in the world's happening here, my second derivative. I take negative 3, substitute into my second derivative, and my denominator I know is going to be positive because it's going to be raised to the 4th power. So my denominator is positive. So negative 3 times negative 2 is 6 minus 4. It's also positive. That means I'm actually concave up. So I'm going to come back here. I'm going to erase this little picture that I have drawn because I want to be concave up instead of concave down. So really, I am increasing, but I am concave up. So increasing, concave up would look something like that. And then let's go ahead and take my test value of 1, substitute into my second derivative. So again, my denominator is positive. So negative 2 times 1 is negative 2, minus 4 is negative. So I am now increasing, but concave down. So increasing, actually I'm increasing both here. And down here I am concave up. And then I am concave down over here. So what does it look like to be increasing but concave down? If we need a little refresher on this, this is increasing concave down, decreasing concave down, decreasing concave up, increasing concave up. So for here, for the second piece, I am increasing but I'm concave down, increasing concave down. So I look something like this at that point. Okay, and last but not least, let's go back to my steps for a minute. Find the x-intercepts and the y, if any, right? So let's find those. That's step 6. I'm going to go down to where I have a little bit of space. And step 6, I go back to my original function to find my x and y intercept. Original function. Because remember, these are points on my original graph that I'm trying to graph with a little bit of calculus. So for my y-intercept, we'll go ahead and let x be 0. Let's go back up to the original function. If x is 0, I get negative 3 divided by 2. Negative 3 halves. And for my other one, let's let the y be 0 so we can find the x-intercept. If I let y be 0, that means what I'm really doing is 0 equals 2x minus 3 divided by x plus 2. If that's the case, then I am going to really be interested in when the numerator is equal to 0. So again, here I'm getting rid of the denominator because I want to know when my numerator is equal to 0. And that will give me positive 3 over 2. All right, so now I have both of those points. And the fun part now, my step 7, is put all this information on the graph. Okay, so here we go. Here's my graph. I'm going to choose a few colors here. Let's use red to draw our vertical asymptote at negative 2. So again, if you have an empty graph that doesn't have any numbers on it, let's use tick marks. There's my vertical asymptote. Oop, almost exactly through there. It's hard to get. I get a little bit close. There we go. Beautiful. There's my vertical asymptote. Let's also do the horizontal asymptote at y equals 2. So again, I'll make a couple tick marks. And there's my horizontal asymptote. I also know that I am going to be, so for my actual function, I'll make my actual function blue. I have a point on my actual function at 0, -3/2, and 3/2. So let's say 0 and then -3/2. Well, if here's -1, I'll make that red again. And here's -2, and then we'll do the same thing on the x-axis. I'm making my function blue, so -3/2 would be about here. And then 3/2 and 0 is about here. And then let's look at my sign diagram. Coming up, approaching -2, so approaching this vertical asymptote, I am increasing and I am concave up. The only way for me to be increasing and concave up would be to be on top of this horizontal function. Notice also that my horizontal asymptote is at 2. That means that as my function approaches -infinity, so when I take my function toward the left, it needs to be getting closer to this horizontal asymptote, and it does. The second part of it, after -2, I am increasing but I'm concave down, and I also have to hit these 2 points right here, my x and my y-intercept. So that means I am increasing but I am concave down, and I am approaching my horizontal asymptote at 2. Again, the other direction, I would be approaching my vertical asymptote. So if I can make that as smooth as I possibly can, I would be increasing concave down, and then on the left, increasing concave up. Okay, we might think there's a lot easier way to do that. Of course there is. However, some of them get very complicated, and we do have to know how to include all these pieces to really analyze the picture. So we are going to do one more together, and then of course we'll have a couple more in class. All right, so our second one I'm going to go through a little bit faster, but you guys are welcome to pause it as you need to. This is the picture now. This is a function now of a linear divided by a quadratic. So notice that your numerator has a degree of 1, your denominator has a degree of 2. That means that when I set my denominator equal to 0, I will get 2 vertical asymptotes. It also means that when you guys take the limit as x approaches infinity, when you have a smaller degree in the numerator, your function will go toward 0. When you take the derivative, and I skipped a few steps here, but when you take the derivative, your x values will actually equal 1 and 5. So I do have 2 critical points here that I want to include in my sign diagram. For the sign diagram, I have a lot of values because I want to include my vertical asymptote at -1 and 2 and my critical points at 1 and 5. So I just link them in order from least to greatest. So the -infinity to the vertical asymptote at -1, -1 to 1, critical point, and so on and so forth. Pick your test value in every single case and plug it into the first derivative. I did not use a second derivative here because I just want to show you guys that you can actually find a lot of information based off of just what you already know about the function. I know I'm decreasing toward -1. Here's my vertical asymptote. I decrease then increase, which gives me a relative minimum at 1, which is where that change occurs. And then I increase and decrease, and that change occurs at 5. If you guys take the 1 and 5 and replace them, substitute them back into the original function, you'll get the points for where that relative min and max occur. And then last but not least, I checked for my x and y intercepts. I put everything on my function, and let's try to actually graph this. I am decreasing from -infinity to -1. The only way to do that would be to be below my horizontal asymptote. I decrease to 1, 3, and then increase again. So I have something that looks like almost a parabola. And then last but not least, I take my maximum at 5 and 1/3. I come from the vertical asymptote, hit that maximum, And now I need to approach my horizontal asymptote.